All right, so we'll talk about auditory sensitivity. So this chapter in particular is going to be talking about absolute thresholds, differential thresholds, talking about intensity discrimination and frequency discrimination as well. So I've got the next 3 classes set aside for topics on auditory sensitivity. So we'll go through the chapter. We'll probably finish up the chapter next time, and then we'll talk about a few different journal articles that go over some topics that might have some kind of relationship to some of the topics that we talked about in here, and we'll have a lab associated with it. So some of the topics we might talk about clinically would be something called brief tone audiometry, which really isn't done anymore. It's kind of an older procedure. The CC, the short increment sensitivity index, again, another older clinical procedure, but we'll talk about those, and we'll probably perform those in the lab, so you can kind of get an idea of what it was like, what its purpose was, and how it's related back to the kind of a more theoretical understanding of some of the psychoacoustic principles. So what is this picture right here on this figure? What does this represent here? This curve, the perceived human hearing curve. I don't even know what that represents.
The normal, how quiet sound can be for a human to hear them?
Yeah, that's right. Those are the sound pressure levels required for an average normal hearing ear to be able to just barely detect them. So of course it's not flat because we're not talking about dB and HL, we're talking about SPL. So yeah, so you can see that for very, very low frequencies that we don't typically test clinically, down to around 10, 20, 30 hertz, we'd require intensity levels close to 80 dB SPL to detect them. So you can see that sensitivity below 125 hertz, sensitivity becomes much, much poorer. It's still within the range of human hearing, but you require much, much higher intensities in order to be able to detect it. And apparently you can even hear some frequencies below 20 hertz down to, I can't remember what it was, down to maybe, I feel like 5 hertz maybe. But it's not really a tonal perception. It doesn't sound like a tone if you heard it down at that low of frequency.
I think the book said 2.
2 hertz, yeah. I was thinking it was a low number, but I didn't want to be too liberal and went down to 2. That's probably right, 2 hertz. Yeah, but it wouldn't sound tonal, I believe, was, I think, the distinction they made. So oftentimes the range that people will talk about is 20 to 20,000 hertz. So if we talk, we already touched on this a little bit when we talk about absolute sensitivity. We're talking about what is the magnitude of the stimulus that's required for that average normal hearing person to just detect the presence of the stimulus. Sounds an awful lot like the definition of a threshold or that we use in pure tone audiometry, just being able to barely detect the stimulus. But as a follow-up from the previous talks on psychophysical methods and signal detection theory, we have to, if we want to define threshold, we probably want to define it in a certain way. We might define it as 50% that the subject would hear and respond to the particular stimulus 50% of the time. So maybe we're interested in the 50% point on the psychometric function. And in this particular example, we can see that 15 dB SPL would be what's required for this subject to respond 50% of the time to that tone. So here are a few examples of psychophysical thresholds, a few examples of absolute thresholds across different sensory modalities or across different special senses. So for vision, vision threshold might be a candle flame 30 miles away. Hearing might be a watch ticking 20 feet away. Smell might be a drop of perfume in a 6-room house. Taste, a teaspoon of sugar in a gallon of water. And touch, a wing of a fly on your cheek dropped 1 centimeter. What do you think all these definitions have in common?
Threshold?
They are all thresholds. Are these being described in a contemporary way, do you think? Or kind of a very old-fashioned kind of way to describe these things? So of course you're going to talk about things in a very different way. Say with vision nowadays, you might be talking about lumens or things like that. But then I'm sure there are other parameters with taste that I don't know how they measure taste, sensory thresholds, but yeah, these are kind of old-fashioned ways of describing them, but very practical ways that you'll understand. So if you had a student who was an introductory student in psychology, probably this would be a very reasonable way to describe sensory thresholds so they could get a good understanding of them. When we talk about absolute thresholds in hearing, there are two main curves that come to mind: minimum audible pressure curves, or MAP curves, and minimal audible field curves, MAF curves. The main distinction between the two is how they're measured. So with these minimal audible pressure curves, that's measured with headphones on. So say TDH 39 headphones. With the minimum audible field curves, measured with a loudspeaker located typically about 1 meter in front of the subject at a 0 degree azimuth and 0 degree elevation. And for the minimum audible pressure curves, there are two types of references you could have there. Probably the more accurate and ideal reference would be to have a probe tube in the subject's ear canal, so you can measure SPL in the ear canal or SPL close to the eardrum. That would probably be fairly accurate. Another way to do it, which is probably a little bit older way to do it, would be to reference dBSPL to a 6cc coupler if you're talking about using TDH earphones. So the author of the textbook, Gelfand, mentions that he would refer to that as a minimum audible, a coupler referenced, a coupler referred minimum audible pressure curve. So it's always when you start getting into kind of the nitty-gritty of these things, dBSPL is not dBSPL. I know when we talk about dBSPL, most of the time we're really talking about dBSPL reference to a certain location. If we're performing real ear measurement on a particular subject, we're talking about dBSPL reference to the eardrum. When we talk about, converting dBHL to dBSPL, like the Audiogram, converting dBHL to dBSPL using a Retspol, we're talking about dBSPL reference to a coupler, 2cc for an insert earphone, 6cc for a supraoral earphone. So minimal audible pressure curves are going to be the dBSPL, or the intensity or sound pressure required for an average subject to be able to just barely detect the sound. So say, for example, we could define it further to say the SPL required for someone to detect it at the 50% point on the psychometric function. Then minimum audible field, the main distinction here is we're talking about the subject is in a sound field and the stimulus is presented from the loudspeaker. But the reference here is not to a coupler. The reference here is to the sound level meter in the place of the subject's head when that subject isn't present. So here is kind of a very, very common type of figure used that shows the kind of an aggregation of a variety of research studies to convey the dynamic range of human hearing. MAP, the minimum audible pressure curve, and right below that, the minimum audible field curve. And then let's talk about those for a moment. There was a brief reference to something they talked about, the missing 6 dB, I think, in the chapter. The missing 6 dB refers to the difference in these minimum audible pressure curve and the minimum audible field curve. Anybody pick up on that at all? So the question would be why with a minimum audible field curve, why is it a lower threshold compared to the minimum audible pressure curve? And they may not have given you the specific reasoning here, but I know they did refer to it briefly, I believe. Did they call it the missing 6 dB? Yeah, part of the missing 6 dB problem. Yeah, here we go. They did mention one of them. They mentioned that physiologic noises would partially mask the signal presented by the earphone, so that more sound pressure would be needed to achieve minimum audible pressure than for the unmasked minimum audible field. That was part of the explanation. The other part was, remember how I talked about the reference point for the minimum audible field curve was the sound level meter in the absence of the subject? Well, then you're not really taking into account the head diffraction effects of having the subject's head present there. And so that partly explains it, and probably also because of the mismatch in the impedance between the ear or the eardrum really, and the earphone when you have a closed system like a headphone on, and you don't have that mismatch in impedance when you have an open system like when there's no headphones in place. And then I believe some of these studies were conducted in an anechoic chamber as opposed to a sound booth. So it was like a combination of different factors which led to the different curves. But it was kind of a big deal apparently back in the I think 70s and 80s when they were talking about it. But you'll notice that what to point out here. Where is human hearing the most sensitive? In what frequency region is human hearing the most sensitive?
The frequency one?
Yeah, frequency range. Yeah, what
Would it be
frequency?
1,000? Or would it be?
Close. I mean, that's pretty sensitive. It gets a little bit more sensitive above 1,000, so probably between 2,000 and 5,000. But yeah, I mean, if you wanted to expand it, it just depends on how wide you want to make that range. But if you expand it a little wider, then certainly 1,000 hertz would fall into that range as well. So yeah, that's yeah. That's partly why that a lot of times our reference we use in audiology is 1,000 hertz, and also in psychoacoustics. That's probably one of the reasons. Another one would be, it's easily detectable generally. That frequency is not a low frequency that maybe wouldn't be quite as alerting. And many people have normal hearing at 1,000 hertz even when they have hearing loss above that. You can see the data they also showed on there for extended high frequency data. So you can see as frequency increases above 10,000 hertz, the SPL required to be able to detect threshold also increases, not nearly as to the same degree as it does for the very low frequencies below 100 hertz, but still the magnitude will increase that you need in order to have a patient just barely detect it. And we talked about this in the OAE class last year, but if you were to, there's a little section here on threshold microstructure. If you were to kind of zoom in on an audiogram and pretend that you had measured the audiogram with very, very fine frequency resolution, say you had measured every 100 hertz or maybe every 50 hertz, you had measured a threshold, and you would get a jagged or kind of a rippling pattern here. And it would be very consistent on retests. So you'd have the same, roughly the same frequencies. You'd have your peaks and dips. You'd have this jagged or rippled pattern, and that's thought to be related to the presence of spontaneous otoacoustic emissions, or thought to be related to the active cochlear mechanism. So it's expected that say you have somebody with sensory neural hearing loss and you do the same kind of test, I would expect that you wouldn't see the same kind of fine structure in that particular group. So if we want to look at the other end of the thing, we know that minimum audible pressure and minimum audible field curves are reasonable measures to use in order to define the lower limits of human hearing. We can also talk about the upper limits of human hearing, and that would be what we normally think of as uncomfortable loudness. But that's not the only way of measuring the upper limits of human hearing. Early on, there was a variety of investigations that used different instructions to the subjects, telling them to respond when they can just feel it, when it tickles, when they feel a prickle in their ear. And so then you can see data is going to be affected by that. But you can see that it's fairly high in general, around 140 dB. 140 dB is, well, that's the upper limits roughly. The probably the largest dynamic range that we could find at any point on this figure would be around 140 dB. If you were looking, say, at the minimum audible field curve, maybe down around 3,000 or 4,000 hertz there, where you see that dip in the minimum audible field curve, and then you might compare it to, say, the tickle curve up top there. So, see, about 140 dB is about the largest that you'll probably see it as. In most areas of human hearing, it wouldn't probably be quite that large. So when you see the 140 dB dynamic range, it's probably a generous estimate of what the dynamic range of human hearing would be. So we don't typically tell people to respond when it tickles or it prickles or they can feel it. We usually tell people to respond when they find it to be uncomfortable. So the exact directions may vary. Actually, I was looking at this particular article the other day, and they compared the categorical loudness rating method that the Cox contour test uses, the 1, 2, 3, 4, 5, 6, 7 that we talked about so much before, and they compared it to a conventional, kind of an old school way of doing the LDLs, where you don't give them any kind of scale, you just have them respond when it becomes too uncomfortable or whatever directions you want to use. And they found that there really wasn't that big of a difference between the two, and so that they were saying that really the old school method would be perfectly fine because it might be a little bit more efficient clinically. But so we can see here, looking at the data for a couple different authors, if we look at the range of human hearing based on clinical data, it looks about like maybe 100 dB or so is the dynamic range that we'd use. It's much easier to see on this type of figure because we've plotted this. Oh, this isn't SPL as well. Yeah, we've limited the range though. We're only talking about 500 hertz to 4,000 hertz. So we're not talking about those frequencies down to 10 hertz or the ones that are much higher than 4,000 hertz. So it takes on a much flatter appearance in the area where human hearing is fairly sensitive. So we can see about 100 dB dynamic range when we look at clinical data. And I know we've talked about Retspols before in class, and I'm sure you've talked about them in Dr. Down's classes as well. But with the whole idea, it's important to mention when we talk about thresholds in dB-SPL, like the minimum audible pressure curves and minimum audible field curves, that we relate them back to hearing level, back to what we talk about with the audiogram. So we can see that these Retspols, these reference equivalent threshold sound pressure levels, are going to be dependent on the particular transducer chosen. So like the TDH39 and TDH49 will have different Retspols. And those are both supraoral earphones. If we compare them to a circumoral earphones that you might use for extended high-frequency audiometry, like the Sennheiser HDA200, again, a different set of Retspols. And then we compare those to the insert earphones, like the ER3As that we typically use, different set of Retspols. And actually, those sets of Retspols are dependent on the exact coupler you use. So there's definitely not one set of Retspols. It's entirely dependent on both the transducer and in some cases the coupler as well. So how do we go from dB SPL to dBHL? How do we use the Retspol to go from dB SPL to dBHL? What do we do with the Retspol to convert dB SPL to dBHL? I mean, if we're going to, like mathematically, in a very simple equation, well, how would we use it? How would we, if I was to give you a value in dB SPL, and I gave you a Retspol, and I said convert it to dBHL, what would you do with it?
Then I subtract it.
Yeah, you'd subtract the Retspol from the dB SPL value. The dBHL values are typically smaller. They would probably typically be no more than, equal at best. Well, yeah, the only exception there would be, you can see with the HA1 coupler on the ER3A, you have some negative values. So in a very rare instance, you would see that dBHL would be higher than dB SPL here. But really, for the vast majority, vast majority of transducers and frequencies, the dBSPL value would almost always be higher than dBHL, so you'd simply subtract the Retspol from the dBSPL value to get to dBHL. And that's also dependent on the standard that you're using. So in the US, we use the ANSI standard, and the ANSI standard may change over time. So these Retspol values are not set in stone. They have changed over the years, and they may change again in future years. There is a concerted effort by a variety of different groups, ANSI and ISO, and ISO being the International Standards Organization, so that's pretty much what everybody else in the world except the US uses. They try to get these things to match up. And the degree of agreement between these two organizations in terms of their standards has improved over time, although it may not always be the same. And here we have a different set of Retspols for the sound field. So for these minimum, say we measure minimum audible field curves, and we want to convert them to dBHL, we've got a variety of Retspols here. Who might we measure thresholds for in the sound field? When would that happen? Clinically?
Children.
Yeah, children. So of course you want to try to use earphones. You want to try to get frequency-specific information, but there's no guarantee that that'll always happen. So if you couldn't get the child to keep earphones on, rather than give up, you might measure their hearing thresholds in the sound field. And what would that represent if you measured hearing thresholds in the sound field for a child? What's that?
Normal hearing in at least 1 year.
If they came out normal, yeah. What did you say, Megan, though?
Just it would represent the threshold of the better.
Yeah, exactly, the better ear. So why do you think we'd have different Retspols for different azimuths, different horizontal angles of arrival? Why would we have different Retspols for different angles of arrival?
That's with I just lost my thought.
Okay.
I had it and then I can't.
You want to describe it, even if you don't know the exact term?
Isn't it like where, like the sound, like say would be the sound coming straight ahead, right?
Sure.
So you have both ears being able to, when it's coming from one side, then it has to take longer to go to the other side?
Yeah, I
Is
mean,
that or is that-
you're on the right track. The key thing is probably going to be diffraction and attenuation.
Yeah.
So that, say, for example, you did mention the binaural monaural one. That's true. So of course, binaural Retspols are going to be different than monaural Retspols because with binaural presentation, you're going to get lower thresholds because of binaural summation. But as far as the azimuth, the loudspeaker azimuth, what we have going on there is, say, for example, the tone is presented at 45 degrees instead of, how about 90 degrees, sure, 90 degrees instead of 45 degrees. So the way the sound is going to diffract on the head and the torso is going to vary. So in the exact resonances that you're going to get are going to vary depending on the azimuth. So it's because of your physical body, essentially, is why we have to have different Retspols for different azimuths. So even for adults, if we happen to be measuring in the sound field, we'd always probably be using 0 degree, I'm guessing. We're talking about kids now because we know for adults we're probably not going to measure pure tone thresholds in the sound field. I guess the exception here would be if you're talking about an adult or child with anotia, right? They don't have any ears, or they have atresia or something like that, where maybe you can't put earphones in there. So in those cases, sure, maybe we're going to measure sound field thresholds. But barring that, for children, how do we have our VRA system set up? Right? Where do we put speakers for VRA usually?
45?
Yeah, probably 45 or 90, depending on just the setup. You might have it at 45, 45, and what would that be? What is it? 315? 45 and 315, or you might have it at 90 and 270. And so in those situations, you've got your different Retspols there. Okay. The same thing here, you're going to basically take the dBSPL minus the Retspol to get dBHL. And there's a little footnote on the bottom here to let you know that these are not for pure tones. These are for either warble tones or FM modulated tones or frequency modulated tones or narrowband noise. And why are we using narrowband noise or frequency modulated tones instead of pure tones?
Because of the steam.
Exactly. So you'll never ever want to use regular pure tones in the sound field. You want to use frequency modulated tones or narrowband noise. And then we've got another set here. Did you guys talk about this one before? I don't think we've talked about it much before. Did you guys talk about this much in Dr. Downs' class?
No.
Okay. So same thing, except this is for bone conduction. And they've got a little bit different name, Retspols instead of Retspols. You've got reference equivalent threshold force levels. So this is a little bit less intuitive. Now the force levels, instead of being, whereas sound pressure level, we're talking about dB sound pressure level reference to, say, a 2 cc coupler or a 6 cc coupler, depending. Here we're talking about dB, SPL, I'm trying to think. dB we're referencing to 1 micronewton, and basically that's measured on a artificial mastoid, which is equivalent to, that's the bone conduction equivalent to an ear simulator, like a coupler ear simulator. Very expensive devices is my understanding, so unless you're doing research in that area, or unless you're really, really big program, then you probably don't have a artificial mastoid all the time. I think our program used to have one many years ago, but it was so old that they couldn't recalibrate it. The price would have been to get a new one, so we got rid of it. But you'll notice that notice you've got two columns here. You've got vibrator on the mastoid, which we're very familiar with. We've got vibrator on the forehead. What are your thoughts on that? Do you guys have any thoughts about vibrator on the forehead versus the mastoid?
It takes more force.
Yeah, it does. It does. Any implications of that, you think?
Farther away. Or
Oh, you're saying why? Sure. But beyond why, what would the result of that be? What are the implications of it? If we're assuming the B71 transducer that we use for bone, then probably a couple things come to mind. One, you probably couldn't test as high of intensities, because if you're just taking the same transducer and putting it on your head, the limit doesn't change, right? The output limit doesn't change for force on those transducers, but you're just taking more greater voltage required in order for you to be able to detect it, really, or in this case, greater force, I guess, is what the voltage is converted to. Well, the other thing would be vibrotactile thresholds. Vibrotactile thresholds will be lower in terms of dBHL because we have larger Retspols. So that's the other problem. There are advantages to vibrator on the forehead, though. If you had the vibrator on the forehead, you wouldn't ever have to switch between the right and left mastoid. You keep it there the whole time. Now, I personally don't know if there's another model besides the B71. I'm sure you could take off the transducer and mount it in a different type of headband, but I honestly don't know if there's another type of transducer besides the B71. But I asked our calibration guy, Jim, who's worked in the field for I don't know how many decades, but he works around Kansas and probably, my guess, a little beyond that maybe. And I asked him if he knows of anybody who has a forehead vibrator for the bone conduction, and he said he doesn't know anybody at all who has them. What about the frequency range? Any thoughts on that frequency range? Do we have, why don't we have higher frequencies on there?
So you can feel them?
Not that as much, because that's the lower frequencies they can feel typically, not the higher frequencies. That was probably a bad question on my part. I probably shouldn't have asked why don't we have higher frequencies on there as much as notice that 4,000 hertz is the limit here. We don't have Retspols for higher frequencies. So just because our audiometer lets you go up to 6,000 or 8,000 on the audiometer doesn't mean you should be testing there. You shouldn't. It's not calibrated there. And there's capable. It's not that it couldn't ever happen, because from my understanding, that they do have bone conduction transducers that are capable of testing up to many higher frequencies, and you can do research studies with them, but there just isn't in the ANSI standard. There's not the calibration available, Retful available for it. So maybe down the road, you never know, maybe we would be testing bone at higher frequencies. Is it valuable or no to test bone at higher frequencies, do you think?
Is it what?
Is it valuable to test bone conduction? If we had Retfuls for higher frequencies, would it be valuable to test bone conduction at higher
For, like,
frequencies?
ototoxic reasons?
For bone conduction?
I don't know. I mean,
Think about it for a moment, though. What do we use bone conduction for, right?
if there's a conductive loss.
Yeah. Conductive losses, where do they typically occur at? Low frequencies, high frequencies, mid frequencies, all frequencies, where?
Low.
Yeah, most of the time low. If it's because there's predominantly a change in stiffness in the middle ear, you'll typically see low frequencies. If that change in stiffness is, as it increases and becomes much, much greater, it expands into the mid frequencies. If you have say for example, you've got changes in both mass and stiffness, that might occur in otitis media with effusion. It might occur in some cases with otosclerosis, right? Because it's not just stiffness, you also have a buildup around the foot plate. So if you increase mass and if you have increases in mass and stiffness, you may see hearing loss at a wide range of frequencies. Do we ever see a conductive hearing loss only at high frequencies? It can happen. It's just very rare. Very rare.
There's collapsed canal.
Collapsed canal, certainly. If there was just a bunch of cerumen in the ear, just a whole bunch of earwax. Maybe if you had like some kind of a pseudotumor in the middle ear, some kind of granuloma in the middle ear where it's not really applying a lot of tension or force onto anything, but it's just increasing the mass in the middle ear cavity, maybe. It's not common by any means, but possible. I don't know how valuable that would be. I suspect it wouldn't be terribly valuable to have it, but it certainly wouldn't hurt anything to have that as another tool in your. Okay, so here we've got on the left side we have DBSPL. We've got DBSPL sound pressure thresholds and DBSPL versus frequency. On the right side we have we've converted those to DBHL. So where would we see the graph on the left side here? Where would we usually see that? Actually, let's go backwards. Let's go with the right ear first. The right ear, not the right ear, the right portion of the figure here. Figure 9.2b. Talk about that first. So that's an audiogram, right? The circles represent normal hearing. The triangles represent somebody who has kind of a steeply sloping high frequency loss, right? So let's go ahead and just look at the audiogram on the right side. You see in DBHL, you've got normal hearing at the circles, and you've got hearing loss with the triangles. And you can see if we change it to DBSPL, the end result in figure A, in panel A there, what do you notice? What are some of the things you notice about converting from the typical DBHL in the audiogram to the representation on the left where it's DBSPL?
Upside down.
Yeah, certainly it's upside down. It wouldn't have to be upside down. It doesn't have to be upside down, but it typically is. So scientifically, the method on the left is the more accurate way to describe it. Really not accurate as much as it fits more with scientific convention to put 0 on the down toward the bottom, and to have as magnitude increases to go to the top. Actually, the audiogram where 0 starts at the top and goes down, that's very peculiar, I guess, in science in general, and that's just basically there's historical reasons behind that as to why it starts 0 on the top. and goes down to 120. If I remember right, I think it has to do with showing somebody basically how much they've lost, kind of a better way to communicate it to patients. But definitely, it could have easily been flipped upside down the other way. So when we go back and forth here, we're simply using the Retspol. We're taking the dBSPL minus the Retspol to get dBHL. But the other thing we're seeing is the ordinate flipped around, flipped upside down there. So with dBSPL on the y-axis, we have it down at the bottom, and dBHL on the y-axis, we have the 0 up toward the top. Where do we? I mean, we know where we use the display on the right. Where do we use the display on the left? Where does that come up in clinical practice?
Earlier.
Yeah, speech mapping. Yeah, that's right. When we're doing an SPLogram, speech mapping, speechogram, whatever you want to call it, there's different names for it. Same thing. But where you're working in dBSPL, and you've input your thresholds in dBHL, and the computer automatically applied the Retspols for you, and then it plots it with 0 on the bottom, 110 on the top, in dBSPL. And then, yeah, that's where we're typically going to see it most often. Flip ahead here. Okay, let's talk a little bit about duration here, effects of duration. There we go. So how does the duration of the sound impact threshold? I think, what did you learn for the duration of a pure tone in audiometry? Like half a second, 1 second, 1.5? What do you guys remember from that? What was the duration of the tone in pure tone audiometry that you use?
I can't say like in seconds, but I like have it in my head of.
Okay, I got you. Your internal representation of it, yeah.
Wasn't emphasized. The length wasn't emphasized.
Was there a minimum that you remember that Dr. Downs told you?
We weren't
Half
given
a
a number.
Really? Okay.
I remember more so in your
It says
clinic.
4 beeps. Yeah.
4 beeps. I don't remember. I mean, you can probably program the duration of those beeps
Yeah.
to be different durations. I'm guessing maybe they're 250 milliseconds, maybe they're 200 milliseconds. I don't know for each of those. Usually, you really wouldn't want to have a duration any less than half a second. Probably, I would say, 3/4 of a second or more. And you're probably not going to want to go longer than 1.5 or 2 seconds. I personally think if I'm holding it down for 2 seconds, that's a long time. I mean, it feels like a long time. So I like 1 second is a good duration. But that's just my opinion. Now, but as far as how does auditory sensitivity affected by duration, anything about a second or greater is basically, you can think of from 1 second to infinity. It's represented the same way. It shouldn't make any difference in terms of thresholds. In theory, I don't know. In clinical practice, that's probably not as much true, but in theory, I think that is true. And in psychoacoustic studies, I'm sure that's true. So anything a second or longer shouldn't have any impact on threshold. But when you start getting significantly shorter than 1 second, then we start to have significant changes in auditory sensitivity, in particular declining auditory sensitivity. So if we look at one end of the extreme, how short can a stimulus be? Well, I mean, it depends on the scale, I suppose. But let's talk about very, very short durations, like less than 10 milliseconds. The issue. Do you remember from Dr. Sin's acoustics class? Do you remember talking about spectral splatter? I'm not sure if that maybe it comes up in ABR or something, but maybe I feel like there was a portion where you talked about maybe duration of the tone, and if it gets too short, what happens is you end up having additional frequency components, side bands or side lobes added. And so what happens when your duration of your signal, your tonal signal even, if it gets too short, then it's actually no longer really a tonal signal. It's going to have energy, and that's a problem actually that comes up with evoked potentials a lot. Not comes up a lot, but it's a big area that historically has had a lot of interest in it because you're taking evoked potentials now, right? Yeah. Okay. So with like ABR, for example, you have to have your tones, your tone bursts, I guess, very, very short. And you have to have them very short so that the waves don't overlap on one another. You can't have it too long. But the problem is if you get too short, now you're no longer frequency specific, right? And so it's this trade-off. It's just this balancing act. So with evoked potentials, as you move from ABR to cortical potentials, you can make the duration of your tones longer because the latency is much longer. So getting back to this, so for short durations, the obvious problem is it's no longer frequency specific. We have transients. So if we talk, and it's not going to sound tonal if it's less than 10 milliseconds either, because it's not tonal anymore, because we have additional frequency components. It might sound like a click. For durations that are greater than 10 milliseconds, it may sound tonal, at least for frequencies above 1,000 hertz. It's going to be a different value. Typically longer durations are required for lower frequencies. But if we talk about just greater than 1,000 or 1,000 above, it just needs to be at least 10 milliseconds, if not greater. But the interesting thing that happens is if we look at the ear, and we look at, say, for example, greater than 10 milliseconds to around 200 milliseconds. We can think of the ear in that range, in those range of duration of tones or signals. We can think of the ear as a temporal integrator. It's going to integrate the energy that occurs within that time frame, no matter where it is. Okay, so for example, you could have all the energy in one burst. It could have one burst of energy at one small little point in time over that 200 or millisecond window, or you could have it spread out. You could have a very, very small intensity spread out over that entire 200 millisecond window, and it could be perceived the exact same way. Let me give you a better description of this. And they call an easy way to think about it is time intensity trading. Now, I feel like time intensity trading comes up a lot in different contexts. It comes up in sound localization. It comes up in industrial audiology in terms of your setting the OSHA requirements or limits. But time intensity trading. So what we mean by this is, say for example, we want to talk about absolute threshold, right? We want to talk about how it's affected. What we can do is if we want to make a comparison, we could decrease the threshold by 10 dB. So improve the threshold by 10 dB if we make the signal 10 times longer. So if we move the signal from 20 milliseconds to 200 milliseconds, that is the same, basically doing the exact same thing as taking the signal which occurs basically within a 1 millisecond time window and dropping it down by 10 dB, or just raising the intensity. So there's a balancing act between the two. So you can do one or the other and get the same end result. If you reduce the intensity by 10 dB, then you also increase the duration by 10-fold. It'll have the same net effect, or vice versa. If you decrease the duration by 10-fold, then you'll need to increase the intensity by 10 dB to have the same net effect. That only occurs within that time window that we're talking about, roughly that 200 to 300 millisecond time window. Does that make sense? Or okay. So I don't have to keep talking about that.
Is that the temporal integration?
Yeah, exactly right. And that's really the basis for brief tone audiometry, which we'll talk about either next class or the class after that, which was they could use brief tone audiometry as some kind of neuroaudiological test to look at neurological lesions and see how they affect auditory function. It really was never that great of a test where you wouldn't have used it like diagnostically, but it was an interesting test to do experimentally in a research context to look at how persons with certain circumscribed auditory lesions were affected. So that's why we need to make sure we have the minimum would need to be about 300 milliseconds for a tone, right? But in reality, we really probably want to have it minimum would be half a second. half a second for a tone if we don't want it to be affected by temporal integration. So here's another way to conceptualize it, kind of the artist's depiction of it, where you can see that energy, if we think of energy as represented by area, if we're talking about it in terms of the vertical axis there, the y-axis, we can think of that height as intensity, and in terms of the x-axis, that width or that length there could be duration of the sound. So we can fit the energy into the same exact box. It's just a matter if we want to fit it vertically, like intensity, if we want to fit it horizontally, like duration. So here, in this particular figure, you can see how frequency is related to temporal integration. We can see that, that really, after about 500 milliseconds, it really doesn't matter because temporal integration is really complete. But up to that point, there is a frequency-dependent effect where there's going to be a steeper slope, or there's going to be greater temporal integration for those lower frequencies. You can see that they go from, say, 12 dB down to 0 for the lowest frequencies, but only from about 7.5 dB down to 0 for the higher frequencies. So greater temporal integration for low frequencies. Steeper slope on that particular function. Okay, so let's move on to differential sensitivity. So differential sensitivity, the key thing here is we're comparing two values. We have a background reference or some kind of initial starting value, and we're comparing it to some kind of variable that we're probably manipulating in one parameter or another. We're maybe manipulating it in frequency, we might be manipulating it in intensity, could be manipulating it in duration if you wanted to. But so we're looking at differential sensitivity. This is what we're talking about when we mentioned earlier, I mentioned, I don't know, a couple classes ago, about just noticeable differences or difference alignments. Those are synonymous, really. They're more or less synonymous. I'm going to probably use the term difference alignments. I think it might be a little more common in audiology or psychoacoustics, and maybe J&D might be more common in other areas of psychology, but I guess I'm not 100% certain of that, but I prefer difference alignments. So if we're looking at what a difference alignment is, or a just noticeable difference is, it's the smallest perceivable difference between two sounds. Now, perceivable on what parameter, that's not specified, but if we're going to talk about the difference alignment in terms of intensity, it would be the smallest perceivable difference in intensity between two sounds, and in terms of frequency, smallest perceivable difference in frequency between two sounds. Notice they're represented for intensity by delta I and for frequency delta F. So delta just represents change. So when you see delta I or delta F, they're typically referencing the difference alignment or the just noticeable difference. So if you were having delta I in dB, it would be just dB. It would not be dB SPL. It would not be dB HL, because you don't have a reference there. You're talking about the difference between two different sounds already, two different auditory stimuli. So it's just dB. And hertz would just be hertz, of course. There's no confusion there. So if we talk about it, we can talk about difference alignments in both absolute and relative terms. In absolute terms, it's pretty straightforward. We just take one and subtract it from the other. So if we're talking about looking for the minimal difference that someone can just barely detect in frequency, you take your comparison frequency and you subtract it from your variable frequency, the one that you're manipulating as the tester. Whatever order you want, subtract one from the other, and that absolute magnitude is your difference alignment for frequency. So that's pretty clear cut. If we're looking at a relative difference, then we want to look at the absolute difference in frequency or change in frequency divided by the starting frequency. So say, for example, we're talking about the difference between, say your starting frequency was 1,000 hertz, and say it takes you up to, you can't tell the difference between the two tones until the second tone has been increased in frequency by 6 hertz, so it's 1,006 hertz. So you'd have 6 hertz, which is your difference alignment, your absolute difference alignment for frequency. You divide it by your starting frequency, which is 1,000 hertz, and then you get your Weber fraction. I know it looks like Weber, but it's pronounced Weber. And so that ratio will not have any units on the end of it. It's just a ratio, 0.004 or whatever the particular ratio comes out to be. So here's an example with frequency. Let's say, for example, it takes us an 8 hertz change in order for us to be able to say there's a difference between 2,000 hertz and 2,008 hertz. So it takes an 8 hertz change. I'm not saying that's what it would, but let's say for a hypothetical subject, it requires an 8 hertz change. So you take 8 hertz divided by 2,000, and you get 0.004. That's your relative difference alignment. So the reason you might want to use a Weber fraction instead of the absolute difference alignment is because the Weber fraction is more or less, given certain constraints, independent of frequency. So a given fraction, like whatever, say it was 0.004, would be more or less the same for 3,000 hertz and 1,000 hertz and 500 hertz and 4,000 hertz. And so it describes a physical phenomena. It takes complex physical or psychophysical phenomena, and it describes them in a simple way, right? That's what we want to do with our data, right? We want to take complex data and crunch it down to a simple conclusion or generalization, if at all possible, so we can make it more meaningful and useful. There's a catch with intensity. Intensity, at least with, if we're interested in intensity specifically with decibels, which we always are with sound stimuli, it complicates things a little bit. So let's first start at the top. Absolute difference alignment for intensity is pretty straightforward. You take one intensity, you subtract it from the other. When I say absolute, I'm talking not about in decibels. I'm talking about, say you take 60 micropascals minus 20 micropascals. So remember, the actual the units of pressure or the units of intensity, whatever your interest is, and you subtract one from the other. We don't do that. We don't typically work in terms of pascals or dynes per centimeter squared or whatever. So let's say, for example, we want to talk about Weber's fraction. Well, we take the change in intensity divided by the intensity. It gives us a ratio. Same thing as we talked about with the relative difference alignment for frequency. But it doesn't tell us what it is in dB. Truthfully, that's what we want. Truthfully, we kind of want to be able to have something in dB. To say that, we want to be able to say that your difference alignment is 3 dB. That's very straightforward. It's very understandable. You're saying that you need you need at least a 3 dB difference between these two sound stimuli in order for you to detect a change, right? If you give somebody a ratio like Weber's fraction, well, that's not terribly meaningful in and of itself. That doesn't help you that much unless you're trying to describe complex phenomena. So what we can do is we can convert it to dB, right? What we do here is we take 10 log, the change in intensity divided by intensity. Remember, the 10 log should be familiar because that's what we talk about in acoustics when you're trying to convert intensity to dBHL intensity level. I think it was 20 log for pressure. But so this is what you'll use here for intensity. But there's still a problem here. If we use this exact formula, 10 log times times change in intensity being like the difference alignment for intensity, divided by the starting intensity. If we do that, then what's going to happen is, if that difference alignment that we've measured in the change in intensity, if that corresponds to an increase that's less than doubling the difference alignment in dB, I'm sorry, less than doubling. If it's less than doubling your reference, your original starting intensity, then that difference alignment you get in dB is going to be negative. Well, how do you interpret a negative difference alignment? Well, you can still use that data, but it's not intuitive. So there's another way we can do it. Now, the book didn't really describe this very well, I'm afraid. They kind of skipped this Weber's fraction part in the middle with the 10 log. They skipped it altogether. They kind of jumped from the top down to the bottom. And so in some sources you might see it as change in I or change in L as well. And so here it's just a small variation on what's above there. 10 log, and then you've got change in intensity divided by intensity, then that's divided by intensity. All right. The reason we've changed it up a little bit like this is so that we don't have any negative dB values, right? We do this to make it more intuitive. Not that we have to do it this way, but it's just a slight derivation of the previous that makes it a little bit more intuitive, a little bit more useful, I think, for people on average, for researchers on average, or clinicians on average. So that's kind of how it goes from Weber's fraction with relative differences in, say, pascals or whatever, down to what we see in terms of talking about difference alignments in dB that are useful. Any questions on that part? Okay, so a little background here. Dr. Weber, he was a 19th century experimental psychologist. So, we're talking about the 1800s, well ahead of his time. He was able to observe that the size of that difference threshold, that JND, was related to the initial stimulus magnitude. So he was really observing that there was a ratio, that if you take that original stimulus magnitude, or the difference threshold rather, and you divide it by the initial stimulus magnitude, you have a constant. That particular ratio we talked about a moment ago, you might talk about it in terms of K, and that would be independent of, say, frequency or whatever. And you can use this Weber's fraction and Weber's law doesn't just apply to hearing. This applies to differences in, say, weight discrimination between two heavy objects, or contrast discrimination between two visual stimuli. Pause that for a moment here. Okay, so like a little 2-minute description of Weber's law here.
Fast lane. Difficult topics explained. The Weber fraction. The Weber fraction was named after the man who discovered it, a German physiologist with time on his hands named Ernst Weber. In studying touch, he found that the percentage of change necessary to perceive a difference between two different lifted weights remained the same across many varying weights. Long story short, he and many others after him determined that the amount of change that can be detected when lifting weights is 2% of the comparison weight. So, for example, pretend you're lifting 100-pound bags of cement. Weber's fraction for weight predicts that if one of the bags had 2 pounds more cement in it, then you'd be able to tell it was heavier. But you could also demonstrate with pennies. Take 50 pennies and weigh them. You'll get 125 grams. That is, if they're all 1982 or newer. Weber's fraction, or the change you'll be able to detect if the comparison sample is 50 pennies, is 2% of 125 grams, or 2.5 grams. So if I take your pennies and bag them into 2 tissues, which is negligible added weight, and I put 50 in one and 51 in the other, and put the 2 bundles of pennies in your outstretched hands, you should be able to tell which one is heavier just by 1 penny difference, or by the Weber fraction for weight for this comparison.
Okay, I know that video was a little bit cheesy, but I don't know, I thought that was pretty interesting as far as in terms of being able to detect changes in that way, putting it in that kind of everyday context, where your ability to discriminate, say, the difference in maybe weight is not a certain fixed absolute value. Like it's going to be dependent on the difference between the two, like a percent difference. So I thought that was pretty interesting. And how could you apply what we talked about with psychophysical procedures to a study like that, where you're comparing two weights? You're having subjects discriminate the difference between two weights. Could we do it the same way, or would it have to be different? Could you use two-interval force choice? In each trial, you have them say which weight is heavier? Probably use it the same way. Use the same exact. You could use the same exact procedures that we talked about too. You could use transformed up-down. You could use PEST. You could use simple up-down, and you could obtain the same point on the psychometric functions. So that stuff carries over very, very well to other areas of psychophysics. So if you decide to leave audiology and go become a psychophysicist, you'll have a start as you maybe study vision or something like that. All right. Move on here. Next one. There we go. Okay. So for intensity discrimination, the experiments early on, there were some problems with the intensity discrimination experiments. So we know they understood the idea of what they wanted to do. They wanted to see, these researchers wanted to see what is the smallest difference that the human ear can detect in terms of intensity. Well, the problem they had was the way that the stimuli were turned on and off were very abrupt. They weren't let's say gated. They weren't, intensity was not gradually increased or decreased, right? It was abrupt, on, off. And if it was abrupt, it creates a transient, which means it's no longer a tonal signal, no longer a pure signal. And so that was a problem. So that was the early 20s. And just a few years later, Rees worked out a clever way to get around that using amplitude modulation. I know talked about amplitude modulation in your acoustics class. And in order to create intensity differences between the two. So the general idea here, I don't remember if you might have talked about this, maybe not, beat frequencies and things like that. Is that familiar at all? Yeah. So you take two sinusoids, for example, that are two sinusoids, same exact magnitude, works fine, and then you vary them in terms of frequency. What you might do is you might give them certain, say for example, you might vary them in frequency. One of them would be like 1,000 hertz, and the other one you might go from 1,002 hertz. Can you detect the difference? No. 1,003 hertz, 1,004 hertz, 1,005 hertz, until they can detect the difference in terms of beats. Because what's happening when you combine those two signals together is they're able to, you're going to have variations in intensity when those two signals are combined together because they don't match up in phase. I'm sorry, the difference between the two will be constant, and you may adjust the intensity of one tone rather than the other. I'm sorry, I said that wrong. So here's an example of two particular tones you might have. So in this particular example, the top one has a little bit greater frequency than the bottom one. No, I can't tell for certain. Well, let's assume right now the top one has a little bit greater frequency than the bottom one, and then you combine them together, and this is the net effect. You'll see the amplitude waxing and waning over time. So you'll have increases and decreases in the amplitude over time, and then you can get around the problem of the rapid onset and offset, which creates transients. Let's see if I've got that here. I thought I had. Guess I don't. Okay. I want to show you something here. There we go. Okay. So we've got the tone on top that's 2,000 hertz. The one on bottom is 2,008 hertz. So let's go ahead and start from the beginning. And let me turn that one way down here. So we can only, it's a pure tone. And then we're gradually going to move it up here on that second tone. And when do you start hearing the beats? Can you hear the beats yet or no?
Yes.
So what about there?
Yeah.
There? Beats going away at all? Yeah.
Yeah, they
But you got the general idea that that you can vary the intensity of that second tone until they start hearing the beats and detect it. So that was the kind of the first way they did it that was actually produced valid data. Okay, let's go back to this. All right. So amplitude modulation is what we were describing on the very top there. So mixing of two tones that are close in frequency in order to achieve beats, and then varying the intensity of the second tone until the subject responds and detects it. The other two methods are going to use pulse tones and the pulse tones with a gated pedestal. That's a very modern way of doing it. And so essentially what you can see is that each of the tones are gated. You have a kind of a gradual rise there. And you'll talk about gating in your ABR class when you talk about like the windowing, like Blackman window and things like that, which talks about the rise and the fall of your tone bursts, or maybe your clicks too. When gating kind of came about, then they didn't really need to use the amplitude modulation tones anymore. So you could have two different tones, and they could be separated by some certain observation interval, and not a problem. So in between, kind of what was more popular, I don't know, maybe 70s or 60s or something like that, was that continuous pedestal method, where the pedestal just kind of means the baseline tone. So you've got the baseline tone in the background constantly going, and then they just add an increment to it. They raise it up. And so that was another way of doing it. I don't think one's necessarily better or worse as far as I know, but they may produce different results. And so that's a problem not just in psychoacoustics, but in psychophysics in general, is that these different methodologies could produce slightly different results. So here's an example of Weber's law, and how, so we've got that 10 log equation that I talked about before, which produces the meaningful difference Lymans in dB, right? So 0 is our smallest there. We can see for white noise, if we're presenting white noise, and we want to see what the minimum intensity difference that someone can perceive is, we can vary the intensity of the second. We can add we can have two different white noise stimuli, and we can vary the intensity difference between the two. We can see that it comes out to be, what is that, a little over half a dB, maybe 0.6 dB, I don't know the exact number, but something like that, for a very wide range of sound pressure levels from 20 up to 90 dB SPL. We see it doesn't hold so well for 10 dB SPL, but in general, because we see all those dots following that horizontal line pretty darn closely, it holds up really nicely for white noise in terms of intensity discrimination, at least for 20 dB SPL and above. But for pure tones or narrowband stimuli, it doesn't hold up quite as well. We can see that similar to white noise, that intensity discrimination was worse below 20 dB SPL. That's true here too. Now this is not quite as clean of a view because you've got 8 frequencies on here, whereas the previous figure we just have the one plot for white noise. But what we can see in particular is that as we move from above 40 dB SPL, especially up at 80 dB SPL, we see that intensity discrimination is much better than expected based on Weber's law. And they call that the near miss to Weber's law. And it doesn't hold quite as well for 8,000 hertz as well. 8,000 hertz is kind of an outlier here, you can see. So Weber's law, in terms of intensity discrimination, holds for intensity discrimination for narrowband stimuli. It holds for like 20 dB SPL and above for white noise. For pure tones, it's more like 20 dB SPL to maybe 50 dB SPL, give or take on that range. And it doesn't really hold for frequencies above 4,000 hertz either. So it's more constraints, more ifs, more clauses there. So here's another way of plotting it. The key difference here is, two key differences here are going to be, the message is the same, but there's two key differences in the figure here. One would be, there's different data plotted here. They're just from different research studies. One for Miller was wideband noise, another one from Verenmeister for pure tones. Same idea behind it, different studies. The other thing is the y-axis is plotted in Weber's fraction, so we can see negative values there. For this kind of study, it doesn't matter, because what we're more interested in is the slope of these curves. So we can see here again, they follow each other fairly closely. About 30 dB SPL and above starts to flatten out. But for pure tones at 80 dB SPL and above, we see intensity discrimination is improving because it's going down. Now, the whole idea that intensity discrimination improves at high sound pressure levels is somewhat counter to what we learned about auditory physiology, because we know that because we have our auditory filters are broadening at high intensity levels, we usually think of poorer frequency discrimination, poor abilities at high levels, not as finely tuned by like the outer hair cells. So they're not exactly sure why it happens, but there's different theories, different speculation behind it. One possibility is that it's related to kind of the spread of excitation along the basilar membrane. So we know that as intensity level increases for a pure tone, it's going to activate across a wider physical region on the basilar membrane. So maybe that's why. That's not the only theory. There's like 2 or 3 other theories out there, but I don't think they know quite yet as to why that happens. So here's an example of where psychoacoustics can inform physiology, because I guess to some extent you could say the behavioral data doesn't really lie. I mean, it's pretty representative, assuming there's not methodological errors. So it may be that we just don't fully understand the physiology as well as we thought we did. I think I already mentioned all of those things, so I'll move on. So remember I mentioned about those methodological differences between the pulse tone method, which had those gated pedestals, and then the continuous pedestal method, which were the two kind of contemporary methods. They were both reasonable, but they'll produce a little bit different results here. So you can see the solid lines represent that continuous pedestal method. So with the continuous pedestal method, the one that's a little bit older but not bad, shows that our difference Lymans are a little bit better than the pulsed method, where they use the gated pedestals. So again, the methods can have an impact on the data in the end. They follow similar patterns, but one just is a little bit systematically. One shows a little bit more sensitive intensity discrimination in humans than others. So that's all I've got for today. We'll finish up next time. We'll try to finish up the chapter next time. We'll be going over frequency discrimination, temporal resolution, and temporary threshold shift, temporal discrimination. And then we'll move on to some articles after that.